All right, everybody, here we go, starting Chapter 7 off with Section 1, which is just on ratios and proportions. Shouldn't be too bad of a section for us. So the first thing we want to do is define what this word here, ratio, means. We're going to be using it a lot during the course of this chapter here. And a ratio, as it says here, is simply a comparison of two or more numbers. Most of the time when we see a ratio, you're just comparing two things, but you can on occasion see what's called an extended ratio that might have more. But usually we're comparing to two numbers right here. So if we were just going to deal with something simple like a series of shapes, and we had a circle and a square and a circle and another square, and then a circle. If we were talking about the ratio of circles to squares, we would simply count the number of circles we have, which is 3, and then we would count the number of squares that we have, which is 2, and write those two numbers next to each other, and there's 3 different ways we can write it. This method right here uses what's called a colon in between the two numbers right there, and that's the way you'll see a ratio presented the most frequently if you're ever reading an article, when they might talk about the ratios of certain economic amounts or something like that in the real world. The second way is the way that we tend to do it the most frequently in a math course, where we tend to deal with fractions. And we like that in math because of all the things that we already know how to do with fractions, and it applies to ratios as well. This third way is one that you'll see more in a writing or a social studies or an English setting rather than in math, where you actually use the word to in the middle. But in all 3 of these cases, we would say it exactly the same way, and this is the way we would actually read that out loud. All of these are ways of presenting a 3-to-2 ratio. It's important to note here that if we were talking about the ratio, though, let's go back to this diagram right over here again. If we were talking about the ratio now of squares to circles, that would flip this ratio around. The number of squares that we have is just 2. The number of circles that we have is 3. So ratios depend on what order you ask for them in. Looking at this diagram again, if you were asked for the ratio of circles to squares, it would be 3-to-2, indicating 3 circles and 2 squares. But if you were asked for the ratio of squares to circles, that would be a 2-to-3 ratio, because you've got 2 squares followed by 3 circles. Okay, now one of the things you're going to be asked to do here a lot is to simplify ratios. And like everything else we do in math, when we deal with a fraction, we always would prefer to deal with that in simplest form because it's the easiest way for us to understand. So let's take a look at what's going on in example A here. If we were in a class with a grand total of, let's add them up, 18 girls and 12 boys in the class, that would be a grand total of 30 students. And if this was the breakdown according to gender in the class, we'd simply count them up and start with this ratio of 18-to-12. But as you guys probably should know by this point right here, you never need permission, you never need to be told. Anytime you can simplify a fraction, you should go ahead and do that. So we would look for a common factor to divide out between 18 and 12, and that common factor is going to be 6. 18 divided by 6 is going to be 3. 12 divided by 6 is going to be 2. So if we took this ratio here and put it in simplest form, we would get the ratio of 3 girls to 2 boys, and you can't do anything else with that, so that's the answer for part A. What that kind of tells you is if you wanted to make, let's say, small groups within the class of 30, you could make every group the same if you put 3 girls and 2 boys in every one of those groups of 5, and then every group would look the same in that makeup. Now, example B is a lot more interesting and a lot tougher than example A right here, because we're dealing with units that aren't exactly what you might expect right here. We're dealing with a ratio of 6 inches to 2 feet. And what a lot of people are going to want to tell me here is that the answer is 3, which they got by taking 6 divided by 2 and getting 3 right here. But that ignores the fact that there are units presented to us here. Inches on the top and feet on the bottom. So as soon as I ask you guys, what's bigger, 6 inches or 2 feet, everybody's going to know that the denominator, 2 feet, is actually the bigger number. And that means that our answer here of 3 isn't correct because we've ignored the units. So what we need to do on a problem like this is convert all of those units into the same unit right here, which means we either need to convert the inches on top into feet to match the bottom, or the feet on the bottom into inches to match the top. Now both of those will work, but the best way to do it is to always convert to the smaller unit. We have inches on top, feet on bottom. Inches are smaller than feet, which means we want everything to be in inches. Now the numerator is already in inches, so we're going to leave it alone as 6 inches and not do anything with that. But for 2 feet, we need to remember that there's 12 inches in a foot here, so 2 feet is going to end up being 24 inches down there on the bottom. Now we didn't change the value of the denominator at all. 2 feet is exactly the same length as 24 inches, but now we've just converted that so that we have apples to apples here in terms of this ratio. So for 6 inches compared to 24 inches, our greatest common factor, again, coincidentally, would be 6. So 6 divided by 6 on top is 1. On the bottom, 24 divided by 6 is 4. And an interesting thing happens here in example B that did not happen in example A. The units, once we converted them, are exactly the same. Inches on top and inches in the denominator. So when you have the same units, they cancel each other out completely, and there are no units in the answer here. So that's interesting. Because example A had different units, girls and boys, we leave those units in the answer. But in B, when we have this ratio of 6 inches to 2 feet, we converted everything to inches, and we ended up with a ratio of 1 to 4, and we don't include any units in our answer here. And I wanted to take just a second and talk about what to do in a case like this in example C. When you've got something like 50 over 5, you could just type this into your calculator, but again, we're just looking for a greatest common factor. The GCF of 50 and 5 is 5, but really we should be reading this just as a division problem. 50 divided by 5 is, of course, just 10. But the interesting thing here is that when we're talking about ratios in Chapter 7 in geometry, we express this answer a little bit differently than we would in just about any other class. In any other math class, if you were presented with this question right here, that would be your answer, and that'd be the end of the story. But if we're talking about ratios, we need to remember that a ratio is a comparison of 2 numbers, and 10 only contains 1 number. So in a case like this, which we wouldn't do in other branches of math, we would go ahead and still include the fraction bar and put the 1 down there on the bottom. So 10 over 1 would be kind of a funny way of expressing an answer in Algebra 1 or Algebra 2 or pre-calculus, but in geometry, when we're talking about ratios, they need to have 2 numbers present. So that ratio ends up being 10 to 1. Okay, let's take a look at what we have going on right here. Now, I mentioned a little bit earlier that most ratios, probably 99% of them, deal with just the comparison of 2 numbers. But once in a while, you see what's called an extended ratio, and that's what's going on here. So the 3 angles of a triangle are in what's called an extended ratio of 2 to 3 to 7. We're supposed to find the measure of each angle. Hopefully once you get the hang of a problem like this, you won't need a diagram, but I think that's probably a good thing for us to draw right about now. I'm going to draw a triangle, and it doesn't really matter how we draw it, but kind of knowing how this problem is going to work out, I'm going to make this triangle look a little bit like this. Now there's 3 angles in this triangle, and the measures of those angles are in a ratio of 2 to 3 to 7. Now, you're going to see problems like this on your homework. Anytime they give you a ratio of measurements, what we're going to do is we're just going to stick an X at the end of each one of those numbers within the extended ratio, so that 2 becomes a 2x, the 3 becomes a 3x, and the 7 becomes a 7x. And these 3 measurements right here are the measures of the angles that we're going to draw within this triangle. So the largest angle, which looks like this one right over here, is going to have a measurement of 7x degrees. The smallest or the sharpest angle, this one over here, is going to be 2x degrees, and the one in the middle is going to be 3x degrees. Now, it doesn't really matter where you put those, but the important thing, and this is some first semester content that I think you guys know, is that in any triangle, when you add together the measures of your three angles, that sum is always going to be 180 degrees. So if we add these three angle measures up, we've got a 2x plus a 3x added to a 7x has to equal a sum of 180 degrees. And from here, it's not too bad of an equation to solve. If we add up our like terms, the 2x and 3x makes a 5x, plus 7x is going to give us a total of 12x, which equals 180. We're going to divide both sides of this equation here by 12, and that's going to tell us now that x is equal to 15. But one of the things I'm hoping you guys learned this year, and if you didn't, it's something we want to try to get down over the summer here, is that in geometry, really in every math class, but especially in geometry, we're not necessarily done just when we have solved for x. So you always want to go back to the directions here and ask yourself, what is it that they wanted to know, and have I given them that answer? And what they said right here to do was to find the measure of each angle, and we have not done that yet. We have just found the value of x. And therefore, we've got to go ahead, let me switch to red right here, and find the measures of each of these angles here. So the first angle out of the three was 2x. Knowing that x is 15, we would get this angle by multiplying 2 times 15, and we would get 30 degrees for the measure of this smallest angle right here. The second angle, 3x, we would take 3 times that 15 right there and get 45 degrees for the measure of this middle-sized angle right over here. And for the third and the largest angle, we would take 7 times that 15 there and get 105 degrees for the measure of the largest angle located right here. So now that we know that, I'll box all of that up, and now we've actually answered the question. Now we have actually found the measures of each of the three angles. So that's the way you handle an extended ratio problem. That always gives people some fits at the beginning of this. Just add an x at the end of each one of those numbers, draw it in the diagram, and do what you would normally do there. Okay, the second big word in this section right here after ratios is the P word, and that word is proportions. So you guys probably got some exposure to proportions in middle school math a few years back, and probably saw a little bit of it in Algebra 1 as well, and of course probably some earlier this year in other spots in geometry. So a proportion here is defined as an equation. That's important. Let me stop right there. A proportion is an equation. So we're going to have an equals sign here. And in a proportion, it's an equation that states that two ratios are equal to each other. And a ratio, as we defined earlier here, is simply a comparison of two numbers. It can be written a lot of different ways, but when we're talking about math, everybody, we like our ratios expressed as fractions. So A over B is just a generic way of writing one ratio would be equal to C over D. That's a way of writing a second ratio. So what we have right here in this box that I'm creating is a ratio or a fraction equal to another ratio or fraction, and that's what we call a proportion. Two fractions equal to each other. All right, and the second thing here, it's not really a theorem, it's not really a formula, it's just an interesting tidbit, very useful here, dealing with proportions. The cross products of any proportion are equal to each other. And what we mean by cross product is that we would take the number in the top left spot of the proportion, which in this case is A, and multiply that by the number in the opposite spot, which is D here, the bottom right. So when we multiply A times D, we just generically get this product right here of AD. Then the second cross product comes from taking the denominator of the first ratio, which is B, multiplied by the numerator of the second ratio, which is C. So we would now multiply B times C together to just get BC. And this property tells us that the cross products in any proportion are equal to each other. So that is an important takeaway here, and that works in absolutely any proportion that we could write. It works all the time, but sometimes it's really easy to see illustrated if you come up with something relatively basic. If I asked you guys, let's go with something like this. If I asked you guys to take a ratio here of, let's say, 10 over 15, That's a fraction, not in simplest form. And if I asked you guys to simplify that fraction, we would look at it and hopefully we would realize, and I don't think we should need a calculator for this one, that the greatest common factor of 10 and 15 is 5. So let's divide that out. The 10 divided by 5 in the numerator is 2. The 15 in the denominator divided by 5 is 3. So this is something that probably a fourth grader could tell us is true here, that 10 over 15 is equal to 2 over 3. Well, if we go back to what we just wrote down, we have one ratio equal to another ratio. That is what we call a proportion. And what we just said a moment ago is that in any proportion, the cross products are equal to each other. So if I multiplied my first cross product, that would be 10 times 3. My second cross product here would be 15 times 2. These two cross products should be equal to each other. Well, let's check it. The 10 times 3 is going to get us a 30 on the left. The 15 times 2 is going to get us a 30 on the right. And last I checked, 30 is equal to 30. Now, you won't see many problems that ask you that right there where the numbers are all given to you, although you will see a few. A lot of the times there are variables involved. All right, let's go back to this slide we were just on a moment ago. So example A asks you the question, is each pair of ratios proportional? It's a yes or no question. So what we really want to know is, are these two fractions equal to each other? And there's a couple of ways to check this, but the most direct way would be to try to use that property we just wrote. If this in fact were a proportion, the cross products would be equal. So we could check this by multiplying 16, the first numerator, by 63. Which is the second denominator. And then we can compare that to the second cross product, 28, which is the first denominator, multiplied by 36, which is the second numerator. So now I'll go ahead and jump to my calculator and multiply 16 times 63. Can't do that one in my head. And I come up with a big product here of 1008. Then my second cross product would be 28 multiplied by 36. Oh, and as dumb luck would have it, I get 1008 for the second cross product. Sure enough, those two cross products are equal to each other. And if the cross products are equal, then we know that these two ratios here are proportional. So this first example, A, is yes. All right, these two ratios here are equal. To kind of put this in context, let's say you were playing basketball and you shoot free throws and you made a grand total of 16 out of 28 total free throws that you threw. A friend of yours practices longer than you do and she makes 36 out of 63 free throws. So the question is, which one of you shot better? You at 16 out of 28 or your friend at 36 out of 63? Well, the fact that these two ratios are proportional, their cross products are equal, says that both of you actually shot the exact same percentage there. That's 16 divided by 28 ends up being about 57.14%, and that's true in both of those cases there. Okay, so that was example 1, and let's take a look at what's going on in example 2. We've got 6 over 11 and then 10 over 18 and 1/3. I can't move this up at all, guys, so I'm going to have to go to a new page to do this. Okay, so the first thing we're going to do is multiply the 6 by the 18 and 1/3. That's going to be a little bit goofy here, but let me write that down. So 6 multiplied by 18 and 1/3. And the second cross product comes from multiplying the 11 times the 10. All right, so 11 times 10 is going to go right here. That right side looks a lot easier. The 11 times 10, just stick a 0 after the 11, and you're going to get 110 on the right side. On the left side, the 18 and 1/3 times 6. Let me show you guys how you might do that on a calculator here. I got to remember where I put all my stuff. There's a lot of calculators you guys can use online. There isn't really a good app for the TI-34 2030 multi-view that a lot of you all are using. So once in a while I'll use this Desmos Scientific Calculator. That's a pretty good one right there. This is a free app, and it tends to work pretty well. So if we wanted to multiply, now I forgot what the numbers were already. If we wanted to multiply 16 times the 18 and 1/3 there, let's see what we've got here. Excuse me, 6 multiplied by, and then 18 and 1/3. Okay, we'd probably want to do parentheses then here. And if you want to do a mixed number on a calculator, the easiest way to do this is to remember that a mixed number is really addition. That's really 18 plus, and then we could put a 1, use my fraction key, and put a 3 right there. Okay, so when I go ahead and hit enter, right over here on this right-hand side, I get that 110. So 6 times 18 and 1/3, I didn't realize this at the time, is also equal to 110. So those two cross products are equal to each other, and that means going back, that example B is a yes as well. That one didn't really look like it because of that ugly mixed number down there on the bottom, but that one works. All right. So that took care of that. I already did that. Let's not worry about that. Okay, here we go. And just about done with this one. What's coming next, though, guys? This is much more in line with what we're going to be asked to do here, to actually solve a proportion. So more often than them giving you numbers and you trying to tell them if it works out or not, they're going to give you two numbers and you're going to have to come up with the value of x in order to figure out what this one is. Okay, so we have a proportion, which they tell us right here, so let's take advantage of the fact that the cross products are equal. Now, I always like to put my x first, so the x right up here, the second numerator, is going to get multiplied by the 13. 13 times x is just 13x, and the second cross product, 10 times 299, is going to be 2,990. And then from there, we would just need to divide both sides by 13 in order to get x by itself. So let's type that in here. 2990 divided by 13 is going to get us 230 for our value of x. So we're going to be solving a lot of equations here, just like we were all year long and in Algebra 1, and we will be doing next year in Algebra 2. And a proportion is just a different way of presenting that equation to you. Let's take a look at one like this here. Okay, in this case, the x is now on the bottom right, but again, I always like to put my x first, so we'll start with this one. 7 times x is going to get us 7x, and the 9 times 56, let's go to our calculators, I think we would probably need to do right there, and get a 504. Those two cross products are equal to each other, and now to get x alone, we would just divide both sides by 7. And that's going to get us x equals 504 divided by 7 is going to be 72. Now, if that example actually seems easier than the one we just did, you're probably right. But the reason that I wanted to put this one here was to point out the fact that in certain cases, and this is one of them, you can actually solve some of these proportions pretty quickly and pretty easily without needing a calculator. If we take a look at the numerators, we have a 7 on the left and a 56 on the right. And if you ask yourself, how did they get from 7 to 56? What they really did is they multiplied that 7 by 8. That got you to 56. Well, if these two ratios are going to be proportional, then whatever number you multiply on your numerators, you have to multiply that exact same number, 8, in your denominators. And if you look at this, the denominator was 9. We multiply that by 8, and sure enough, 9 times 8 would have told us that x was 72. So this is a way you can solve a lot of proportions without needing to be dependent on a calculator. All right, so that was example 2. Let's look at example 3. And this is a tougher one now. It does contain variables here, but we got a little bit more going on right here in terms of binomials. All right, but again, two ratios equal to each other. So this is a proportion, and we're going to go ahead and we are going to still cross multiply here and see what we get. So the top left, which is 4, is going to get multiplied by the bottom right. But the mistake that people make a lot of the times here is they multiply the 4 times the 3x minus 1, and they forget that every time we go to multiply a monomial by a binomial, we've got to put parentheses around that binomial, and we have to use the distributive property here on that side. Okay, so that's the top left times the bottom right. That's going to equal the bottom left, which is 5, multiplied by the top right, which is 2x plus 2. And again, a monomial times a binomial, we have to put parentheses around the binomial and then use the distributive property. It's one of those things, as soon as you see the parentheses, everybody knows to use the distributive property, but a lot of people put it there that way. Okay, let's multiply it out. The 4 times the 3x is going to be a 12x. The 4 times the minus 1 is a minus 4. Equals 5 times 2x is going to get us a 10x, and the 5 times 2 is going to be a 10 there. Okay, a little bit of work to do here. Let's get all of our x's on one side, so I'm going to subtract a 10x from both sides. Since all of my x's are moving to the left, I'm also going to try to move all my constants, my non-variable terms, to the right side. That means I want to get rid of that minus 4 by adding a 4 on the left, and we'll balance that by adding a 4 on the right. Now, I'm not sure who you guys had for geometry this year. Your teachers may or may not have shown you that trick of doing two things at once. I like to do that a lot. You're going to see your Algebra 2 teachers doing it a lot next year. So what happens? On the left side, we have a minus 4 and a plus 4. Those cancel. On the right side, we have a 10x and a minus 10x. Those cancel. So on the left, we have a 12x minus 10x, which leaves us with a 2x, equals 10 plus 4, which is 14. Now we're going to quickly divide both of those sides here by 2, and it looks like we have an answer now of x is equal to 7. One of the things we would always like to do if we can is take that answer and plug it back into the original equation and find out if it works. So let's see what happens here. If x is 7, right here we have a 2 times 7, which is going to be 14, plus 2 is going to get us a 16 in the numerator. Down in the denominator, a 3 times 7 is 21, minus 1 is going to get us 20. And 16 over 20 is a ratio that can certainly be simplified. Those two numbers have a greatest common factor of 4. Dividing the 4 from 16 gives us a 4 on top, and in the denominator, 20 divided by 4 is going to get us 5. So what are we saying? 4/5 is eventually equal to 4/5. And as long as we end up with the same fraction both times, we're in good shape. All right, guys, that's everything we're going to do here for section 7.1. So now that you're done watching this, you're going to go find the 7.1 worksheet that's posted on our classroom page, and you're going to get working on that. Okay, sounds good, and we'll pick up on 7.2 in our next section.